Hello everyone, I am Naveen G. As a part of Machine Learning Foundations for Project Managers assignment, let us build a model to predict the electrical output of a combined cycle power plant. The objective of this assignment is to build a model to predict the electrical energy output of a combined cycle power plant. We have been provided the structured data, that is input features such as temperature, ambient pressure, relative humidity, exhaust vacuum, and the target value, that is electrical energy output. To create a model, we will follow the CRISP-DM process, which basically involves business understanding, that is understanding the problem, the outcome measures to be used, then data understanding, then we have data preparation, modeling, evaluation, and then finally the deployment. Components of the model will involve selecting the feature which we want to use, select the algorithm, select the hyperparameters for our algorithms, and then finally select the measure. Our first step in CRISP-DM process is business understanding. It is important to understand the business outcome that is expected out of this model implementation. Though this is not specifically asked for in the assignment, from the problem statement it is clear if we can predict the energy output accurately, then outcome could be lower cost per megawatt hour of power produced or lower emission rate per megawatt hour of power produced. Out of the suggested methods to create this model, we'll use the Excel method, which does not require any programming to be done. Our next step is data understanding. Let us understand the available data. And based on our understanding, we'll select the algorithm and the output metric that we will use for evaluation. Data provided to us is a historical data with 4 features and a target value, which basically points us to a supervised learning approach. Our objective is to predict the electrical energy output, that is, predicting a numerical target, which basically points us to use regression algorithm. Based on above understanding, we will use supervised learning algorithm, and we have below choices for it, that's linear regression, ridge regression, or lasso regression. We'll use the output metric R square as a coefficient of determination, which is readily available in Excel, and this will provide a measure of how well the observed outcome are replicated by our model. Continuing our data understanding step, we'll understand the data provided and select the features for our model that can give us a most value. We'll use the visualization to understand the relationship between the features and target, and a statistical correlation value to select a feature. I have used a scatter plot and a trend line feature from Excel to understand the relationship of target with each individual feature. Also, we have calculated the R square value to help us in identifying the relationship statistically. The first plot here depicts the relationship between the energy output and temperature. it is visually clear that it has a strong linear relationship, and it is justified by a high statistical value of R square, which is 0.89. At this stage, we also tried a polynomial trend line to check if it better fits. R value in case of polynomial fit is 0.90. There is no significant improvement, so we'll stick with our linear relationship, which is more simpler. The second plot depicts the relationship between energy output and exhaust vacuum. This is visually clear that it has a linear relationship and is justified by a statistical value of R square, which is 0.75. However, this is not as high as our first plot. We also tried a polynomial trend line to check if that fits better here. R square value in a polynomial case comes out to be 0.77. Again, there is no significant improvement here, so we'll stick to our linear relationship, which is much simpler. Coming to other two features, the first plot depicts here the relationship between energy output and atmospheric pressure. This is visually clear that it has no clear relationship, and it is justified by our low statistical value of R square, which is 0.27. The second plot depicts the relationship between energy output and relative humidity. Again, this is visually clear that it has no clear relationship, and it is justified by our low statistical value of R square, which is 0.14. From all these four plots, it is clear that feature that can give us a most value are temperature and followed by a exhaust vacuum. We'll select these two features to start with and then compare it with the full feature model. Come to our next step, that is finalizing our model. From our data understanding, we have found two of the features, that is temperature and exhaust vacuum, have a strong relationship with the target. However, other two features, that is atmospheric pressure and relative humidity, does not have a strong relationship with the target. Using lasso or ridge regression would have proved this for us. However, considering only the linear regression capability available in Excel, we have manually created two models. Model 1 considering all the input features, and model 2 considering only the features that have a strong relationship with the target. Indirectly, it will reflect the lasso as we have manually eliminated the unimportant features. And we'll evaluate these two models and select the one that gives us better results. Our next step is evaluating our models. We have all the data to proceed with evaluation. However, we'll split our data to help us in validating our models and select the best one. First, we'll split the total data into a training set and test set. This will be a split of 90% and 10% respectively. Then we'll split the training set into a sub-training set and a validation set with the split of 80% and 20% respectively. We'll use a fixed validation set with the 20% of validation data, which comes to close to 1722 samples. We have big enough data samples to go ahead with a fixed validation set instead of k-fold cross validation, which could have been an option for a small data set. As a part of evaluation, we'll first select the preferred model based on our validation results. Statistical analysis of the predicted values from our model for the validation data is depicted in this slide. We can see that model 1, which uses all the features, has marginally better value of R square, that is 0.93, versus the model 2, which uses only two features, where R square value is 0.91. Considering very marginal value add, we can go ahead with a simpler model 2 with only two features. However, considering the requirement of the assignment of selecting a better performing model as per the metric, it's a model 1, though it's very marginally better. We'll move ahead with model 1 for further evaluation with our test set. Final evaluation of our selected model 1, which uses all the features, is depicted in this slide. We have retrained our model 1 with full training set, that is our sub-training set plus validation set, that is 90% of the data, and then evaluated it with a testing set data remaining 10%, and the R square value that we obtained is 0.92 for the predicted data by our model. This is very close to the R square value of the training set, that is 0.92. Some of the test sample data and its predictions by our model 1 are depicted here. We can use this model 1 for deployment, or we can select a model 2 with marginally lower performance but much simpler to implement. That brings us to end of this presentation. Thank you for your time.